Howdy. Today we're going to be going over how to create a simple 2D wind tunnel simulator. I came across this video here, and it's linked in the description along with the original code. And in this video, I thought it would be useful to go over the principles and the math involved in the code, and then how we can modify it to create a wind tunnel so we can see simple flow patterns of objects obstructing the flow. To start off, we're going to need some governing equations. We know we need to ensure mass conservation for this to be physically possible, so we'll use the mass continuity equation here. And for fluid movement, we can use the Navier-Stokes momentum conservation equation. We're going to simplify it by quite a bit with some assumptions about the fluid we're modeling. First, we're going to assume inviscid. This removes the viscosity term. Next, we're assuming no body forces. This removes the force term. We can do this with air, but if you're modeling something like water, then gravity does play an actual role, so in that case, you would need it to remain. Lastly, we assume the fluid is incompressible. This fixes our density to remain constant, thus reducing the complexity of this differential equation. That last assumption is going to be key in the mass conservation, because now that time-dependent term falls off, since by incompressible definition, it does not change with time. And then dividing by the density through, we get a simpler version of the continuity. So according to this equation, we need our divergence of the velocity to be 0. And in this vein, we need to invoke Helmholtz and Hodge's decomposition theorem, or also known as the fundamental theorem of vector calculus. This theorem states that any smooth vector field can be broken down into two vector fields, a gradient field of a potential function and a divergence-free field. And you guessed it, we want that last one. Here, our potential function would be the scalar pressure field, and W would be our starting velocity field of this time step. So rearranging, we see our only unknown is the pressure field. One easy way to solve for it is to multiply both sides by the nabla operator. Since we know the divergence of U is 0, that drops off, and we're left with this Poisson equation where we have some choices of how to solve it. And for this video, we'll be going with the Jacobi iterative method of solution. Just before we get into that though, we need to set up the area of testing for calculations. This is done by discretizing the space into an equal spacing grid. This equal spacing will help out later. We will go with the central finite method. This is where we use the center of the elements for calculations. There are other methods such as the staggered, but we will use the central. We index the field as such. Now, with this grid, we can start to discretize our equations. Starting with our divergence of the starting velocity field at this time setup, this is the equation for divergence in the central finite space. In Matlab, we can just take the divergence directly with this function, but we need to add the 1/2 since we're doing it in finite discretization. And for the Poisson equation, we can expand it out a bit, and now we can apply the central differences to it. We now have this, but since we have equal spacing, delta x and delta y are equal. This simplifies down to here. And with this, we want to know the pressure at the central element, so we solve for the ij term. Taking a look at the grid of this equation, it is telling us we need to take the value from each side of the central cell, and then take the average of them and put it into that central cell. This method can be done with a double for loops, but a faster method in Matlab would be use the convolution function, where we create a stencil to represent this part of the equation. This code would look like this. But currently, this is just for Poisson equals 0 solution. We want Poisson minus the divergence of the velocity equals 0 solution. For this, we can simply subtract the divergence term we found earlier in each iteration. This will loop as many times as you like for accuracy, but as it is tied directly to the speed of the simulation, you might want to try to find a reasonable balance. So now that we know the pressure, we can go back to this equation, plug it in, and solve for the divergence-free velocity. Now we can perform the advection process. This part is pretty straightforward except one thing. We're not advecting forward, but backwards. When advecting forward, there's a stability condition that the time step needs to be smaller than the grid spacing divided by the magnitude of velocity, or it may blow up and break the simulation. One fix for this is to take a time step backwards, which now it'll be unconditionally stable, which is very good. The time stepping backwards can be thought of as this. If we have a boat traveling along a river, to know where it is going, we can look back to see where it has been. Through the methods of characteristics, we can know that along this streamline, or in this case the river, all future location and velocities can be known based on the initial field and characteristics. So, for a location, we trace back along the characteristic. Then we evaluate the initial field at the prior location and use this velocity for the new velocity. This can be done with your favorite methods such as Euler's method or even Runge 4, as the video I referenced had used. Runge is a bit more accurate than Euler's, but Euler's is simple and slightly faster, so it's up to you. Here's the code for both. So at this point, we have an advecting, practically divergence-free flow. Now we need to control it. Here's where our boundary conditions come into play. Starting off, our velocity and pressure within the tunnel will be 0 for all cells. Next, we need to choose if we want a no-slip condition on the top and bottom walls or not. If you do, then at the beginning of each step, we need to set the Vx and Vy for all of those cells to 0. If you do not want them to be there, there will be a slip at the top and the bottom, which will act more like an unmoving stream tube, which is not all that physical, but is an option if you want. Next, within the Poisson solver, we need to make sure our pressure boundary conditions are set each time. For a wind tunnel, we need the direction of flow, so we need a difference in pressure from the inlet to the outlet. We can set our outlet cells at 0 and our inlet cells to anything above 0. This is what we will use to control the speed of the tunnel. The higher the difference in pressure, the higher the velocity. Now for the walls, we need the outermost cells to be equal to the cells directly above or below them. This will create a situation where the flow cannot go into the wall, but only along it. At this point, we have a wind tunnel that we can see the velocity change in as time progresses. It has a starting value of 0 everywhere, so it will take a few seconds to find its stable velocity, since the pressure is bouncing back and forth in the tunnel until it also stabilizes. If you want to see particles, you can do this with a forward advection from either your Euler or the RK4 method. Now, adding an object to the flow is not so hard. You just need to ensure 0 velocity for the body the object has. In Matlab, it is easiest to set a mask to the object. You can either do it algorithmically and define the mask, or you can just doodle it in an Excel and then pull the data from Excel into Matlab. There are a few ways to visualize the flow. You can watch the particles advect around, but this only gives sight to the streak lines from your originating point. Nonetheless, it does look good. You can see the velocity field by taking the magnitude of Vx and Vy, and this lets you see all points. But my favorite would be the absolute value of the curl of the velocity field. It gives this actual fluid-like visual. You can also not take the absolute, and then you can see the positive and negative vortexes. So I would like to thank Robert for his video and code. It was great learning more about this topic, and he has other videos showcasing his animations on programs such as Blender, so go check it out. So finally, there are other, and I mean a lot, of other methods to simulate flow in CFD, and I hope to get into those methods as well. Thanks for listening, and have a good one. And here are some animations just for fun.